Okay, let's talk about primes, LCM, and GCF. A prime number, or prime, is a natural number greater than 1 that has no positive divisors other than 1 in itself. Example: 2, 3, 5, 7, 11, 13, 17, etc. are all prime. Please note that we did not list the number 1. It is not a prime number. It only has one factor, not 2. And the only even prime number is the number 2. A prime factorization of a natural number is the number written as a product of prime numbers. Let's see. The prime factorization of 12 is 2 times 2 times 3. 2, 2, and 3 are all primes that multiply together to give us 12. Example: let's write the prime factorization of a larger number, 3,500. The method I will encourage you to use is repeated division by prime factors. Start by dividing 3,500 by the smallest prime factor, which is 2. 3,500 divided by 2 equals 1750. Keep using the number 2 until you cannot use it anymore. 1750 is even, so we can divide it by 2 again. 1750 divided by 2 equals 875. 2 will not work anymore. Okay, it's not even. So let's try the next prime number in order. Let's try 3. By adding 8 and 7, you get 15, and 5, you get 20. Those are the digits in 875. They do not give us a number that is divisible by 3, so 3 will not work. But 5 will work. 875 divided by 5. We know that'll work because 875 ends in a 5. We get 175. This number also will be divisible by 5. 175 divided by 5 equals 35. This number will also be divisible by 5. 35 divided by 5 equals 7. 5 won't work here, but we know that 7 is prime, and it's the next prime number that we need to divide. Continue until we divide the quotient is 1. 7 divided by 7 equals 1. We have prime factored 3,500. The prime numbers are 2, 2, 5, 5, 5, and 7. And if we want to see if it works, we go 2 times 2 times 5 times 5 times 5 times 7. And we get the same thing as 2 squared times 5 cubed times 7. And if you do the math on that, you will get 3,500. Write the prime factorization of 3,500 using a factor tree, another method. Take 3,500 at the top of the tree. It's divisible by 2. And if you go 3,500 divisible by 2, you get 1,750. We know that already because we've done this already. Now we take 1,750 and divide it by 2. Notice that we bring the 2 down. 1,750 divided by 2 is 2 times 875. We bring the primes down with us on the tree, building our base. 1,750 divided by 2 is 875, so now 875 is not divisible by 2 or 3, so we go right to 5. 875 divided by 5 is 175. Again, note we bring the primes down. 175 is also divisible by 5 again. 175 divided by 5 is 35. And again, 35 is divisible by 5. 35 divided by 5 is 7. Once we hit 7, we know that 7 divided by 7 is 1. We're going to get 1 there. We have our primes listed right across the board here. 2 times 2 times 5 times 5 times 5 times 7. Or 2 squared times 5 cubed times 7 gives us our number. Example 2. Write the prime factorization of 2,646. So in example 2 here, we want to write the prime factorization of 2,646. Start by dividing 2646 by the smallest prime factor, which is 2. 2646 divided by 2, we get 1323. An odd number will not be divisible by 2, but we can figure out if it's divisible by 3 by adding the digits in 1, 3, 2, 3. What do we get? 1 plus 3 is 4, plus 2 is 6, plus 3 is 9. 9 is divisible by 3, therefore 1323 is divisible by 3. So we use that one next. 1323 divided by 3 equals 441. Let's try that method again to see if 441 is divisible by 3. 4 plus 4 is 8, plus 1 is 9. Yes, 9 is divisible by 3, so 441 is divisible by 3. 441 divided by 3 equals 147. 1 plus 4 plus 7 is 12. Again, divisible by 3 will be divisible by 3. Here we go. 147 divided by 3 equals 49. 4 plus 9 is 13, not divisible by 3, so we cannot use 3 anymore. We cannot use 5, but 7 will divide 49 exactly to 7. Now we need to get 1 as our final answer, so 7 divided by 7 equals 1. Now we can circle or square up our prime factors, 2, 3, 3, 3, 7, and 7, and write them as a product of primes. 3,500 equals 2 times 3 times 3 times 3 times 7 times 7, which is the same thing as 2 times 3 to the power of 3 times 7 to the power of 2. The greatest common factor of 2 or more numbers is the greatest factor the numbers have in common. Let's discuss that a little further. Example. Given the greatest common factor, determine the greatest common factor of 126 and 144. List the prime factors of each. So 126 divided by the prime 2 and 144 divided by the prime 2. We get 63 and 72. Let's now prime factor 63 using 3. 63 divided by 3 is going to be 21, but 72 can be divided by 2 again, so we're going to get 36. So now we're dealing with 21 and 36. Let's use 3 and 2 again. 21 divided by 3 and 36 divided by 2, we get 7 and 18. 7 will not be divisible by 3, but we know it's prime, so the next prime for it is 7. But 18 will be divisible by 2 once again. 7 divided by 7 and 18 divided by 2, we get 1 and 9. We're done with 126, but we got to keep going with 144 because 9 is still not broken down to 1. Let's prime factor 9, okay? 9 divided by 3. Well, that'll work. We get 3. We still haven't got the 1 that we're looking for. Take 3 and divide it by 3, and we get 1. Now we can list the prime factors of 144. We've already listed the prime factors of 126. They are 2, 3, 3, and 7. And the prime factors of 144 are 2, 2, 2, 2, 3, and 3. Write them horizontally as a product of primes. 126 equals 2 times 3 times 3 times 7. 144 equals 2 times 2 times 2 times 2 times 3 times 3. Or, now that we have them listed that way, take out the common factors in both. 2 times 3 times 3 is common in both. 2 times 3 times 3. Multiply those together and we get 18. This is our greatest common factor, or GCF, for 126 and 144. Example 4. Determine the greatest common factor of 120, 150, and 210. Again, list the prime factors of each. For 120, divide by 2. For 150, divide by 2. And 210, divide by 2. We get 60, 75, 105. Now looking over these three numbers, the only one that can be used with 2 again is 60. The others, we're looking at 3 for 75, and we're looking at 3 for 105. Let's check that out. 60 divided by 2, 75 divided by 3, and 105 divided by 3. And we get remainders of 30, 25, and 35. Now look over at the 30. It can be divisible by 2 again, But 25 and 35, we're looking at 5 on both of those. 30 divided by 2, 25 divided by 5, 35 divided by 5, we get 15, 5, and 7. Well, for 150 and for 210, 5 and 7, we're down to prime numbers that we can divide into to get our 1. But 15 for the number 120, we can prime factor that a little more by using another 5 or another 3. 15 divided by 3, and now we take 5 divided by 5 and 7 divided by 7. We get 5, 1, and 1. We can now square up with our prime factors of 210 and 150. For 210, we've got 2, 3, 5, and 7. For 150, we have 2, 3, 5, and 5. We can go a little bit further with the 120 primes by dividing 5 divided by 5 to get 1. Now we have our prime factors for 120, 2, 2, 2, 3, and 5. List them horizontally as a product of primes. For 120, we get 2 times 2 times 2 times 3 times 5. For 150, we get 2 times 3 times 5 times 5. And for 210, we get 2 times 3 times 5 times 7. In those groupings, take out anything that's common. 2 times 3 times 5 is common in 120. 2 times 3 times 5 is common in 150. 2 times 3 times 5 is common in 210. Do the math, and our GCF is 30 for the numbers 120, 150, and 210. The least common multiple of 2 or more numbers is the least number that is divisible by each number. Let's talk about that. To determine the LCM, you can use this formula. LCM of A and B is equal to A times B divided by the GCF of A and B. So, in our example, determine the LCM of 10 and 15. Here's our formula. LCM of A and B is equal to A times B divided by the GCF of A and B. Fill in for A and B. A is 10, B is 15. So LCM of 10 and 15 is equal to 10 times 15 divided by the GCF of 10 and 15. We get 150 divided by 5, and that's going to equal to 30. Example 6. Determine the LCM of 28, 42, and 63. Another method of determining the LCM is to find the prime factorization of each number and take the product, each prime factor, the greatest number of times it occurs in any of the numbers. Example. Determine the LCM of 28, 42, and 63. 28 divided by 2, 42 divided by 2, and 63 divided by 3. We get 14 divided by 2, or 20 divided by 2 is 14, 42 divided by 2 is 21, and 63 divided by 3 is 21. Going further now, the 14 can be divided by 2, the 21 can be divided by 3, and the 21 over here can also be divided by 3 to give us 7, 7, and 7. Now, divide 7 by 7, another prime number, 7 by 7, 7 by 7, and we end up with 1, 1, and 1. Circle up our prime factors. For 63, we have 3, 3, and 7. For 42, we have 2, 3, and 7. And for 28, we have 2, 2, and 7. All prime factors of these numbers. Listing them horizontally, 28 is equal to 2 times 2 times 7. 42 is equal to 2 times 3 times 7. And 63 is equal to 3 times 3 times 7. Take the product, each prime factor, the greatest number of times it occurs in any of the numbers. So in the first one, 28, 2 repeats itself 12. There is the greatest number of times, 2 to the power of 2. In 42, we have just 7, the biggest prime factor. In 63, we have 3 to the power of 2, which is our 9. LCM is 2 to the power 2 times 3 to the power 2 times 7. Do the math. 4 times 9 times 7. 252 is our LCM of 28, 42, and 63. Example 7. What is the side length of the smallest square that can be tiled with rectangles that measure 18 centimeters by 24 centimeters? Assume the rectangles cannot be cut. Good idea to draw a picture. So we have a square, and inside that square we have rectangles that are measured 18 by 24. We'll need the LCM of 18 and 24 if they are both to fit perfectly in our square. 18 broken down in prime factors is 2 times 3 times 3. 24 broken down to prime factors is 2 times 2 times 2 times 3. Circle 3 times 3 and 2 times 2 times 2. LCM of 18 and 24 is 2 times 2 times 2 times 3 times 3, which is 72. The smallest square is 72 centimeters by 72 centimeters. Example 8. What is the side length of the largest square that could be used to tile a rectangle that measures 18 centimeters by 24 centimeters? Assume the squares cannot be cut. So now we have a rectangle diagram, and inside that rectangle we have little squares. Now a square, remember, the sides are the same, so we're going to list them as X and X. But our big rectangle, it measures 24 by 18, or 18 by 24, however you look at it. Now the value of X must go into both 18 and 24. So we are looking for the GCF. Prime factor 18 and 24. Prime factor 18, we get 2 times 3 times 3. For 24, we get 2 times 2 times 2 times 3. Circle our common primes, 2 times 3 and 2 times 3. The largest square is 6 centimeters by 6 centimeters. That takes care of primes, LCM, and GCF.